Any problems, look for us. One of our staffers, many of them are wearing like a yellow T-shirt. So we will have a YouTube a streamcast, and we will give you the links to distribute as you see fit. And also, there is a dinner this evening. And so please try to be here, and we will guide everybody to dinner. The dinner will be at 5:30 this evening. And finally, there are no COVID restrictions legally. We have put a rapid test in everybody's bag. Anybody who feels sick, please test yourself and inform us if you are actually sick. Thank you very much. And we should be turning this over to the program chairs. Guy?
Okay, so hi everyone, welcome. And we'll keep this short and sweet. So we just want to welcome everyone. Thank you all, to everyone who submitted their work, to the speakers, to everyone who's attending the conference, and especially thank you to the general chairs for this beautiful organizational job, and to all the local staff and volunteers who have been helping out. And Hotek, would you like to add some words of wisdom? Shall we?
You'll hear more from us at the business meeting.
Okay, so without further ado, we can move to the first session. So where's Noam?
Now, session chair is Prashant.
Yeah.
You don't need to come up.
Hi everyone, welcome to this rather impressive hall. And we start with the talk that I've been looking forward to hearing. This is about constructing PRGs from one-way functions by Noam Mazur and Rafael Paz, and Noam is giving the talk.
So I'm going to talk about the construction of pseudo-random generators. And as we all know, one-way function is the minimal assumption in cryptography. One-way function is a function which is easy to compute, but hard to invert. And most of the cryptographic primitives imply one-way function. But more importantly, we can use one-way function in order to construct many useful primitives, such as encryption scheme, signatures, and more. And one such important primitive is a pseudo-random generator. So there is the amazing result of Astad, Impagliazzo, Levin, and Nubi that show that we can construct pseudo-random generators from one-way functions. And since then, there was a long sequence of work that both simplifies the construction and the proof, and get better efficiency in terms of the seed length and the number of calls to the one-way function. But still, the proof of this theorem that one-way function implies pseudo-random generators is hard to teach. And the goal of this work is to give a simple proof or a simpler proof, at least for the non-uniform settings, in which we start with a one-way function which is secure against non-uniform adversaries, and we construct pseudo-random generators which is secure against non-uniform adversaries. And quite surprisingly, along the way, we also get slightly better parameters. So how do we prove that one-way function implies pseudo-random generator? The general approach is to first start with a weaker notion of pseudo-randomness and show that we can construct this weaker notion from one-way functions, and then to amplify this weaker notion into pseudo-randomness. And Astad, Impagliazzo, Levin, and Luby use the notion of pseudo-entropy as the weaker notion, and Eitner, Reingond, and Vadan use the notion of next block pseudo-entropy. Both these notions are very elegant and beautiful notions that have have uses in other contexts. But the key insight of this work is to come up with a more simpler weak notion of pseudo-randomness, which is just counting unpredictable bits. So what do I mean by that? So let's X be a distribution over n bits. Bloom and Micali defined the notion of next bit unpredictability. And they said that we say that a random variable over n bits has next bit unpredictability if when we read X bit after bit in an online fashion, in each point, given the prefix, we cannot predict, a polytime Turing machine cannot predict the next bit in advantage more than half plus negligible. And Yao proved that if a distribution have this property of next bit unpredictability, then this distribution is pseudo-random. So if we want to construct pseudo-random distribution, it's enough to construct a distribution with next bit unpredictability. In this work, we consider a weaker notion of unpredictability, for which we call bits unpredictability. And we only require that some of the bits are unpredictable. So instead of requiring that for every index I, given the prefix, we cannot predict the next bit, we require that there is some set of indexes, such that for every index in this set, we cannot predict the bit given the prefix. So if we read the distribution bit by bit, there is some of the bits that we cannot predict. And we let the set S to be a random variable that can be jointly distributed with X. And we want the size of this set to be as large as possible. This is what we measure. This is what we care for. So this is bits unpredictability. And the proof overview is first construct bits unpredictability from one function, or a distribution with bits unpredictability from one function, and then converting bits unpredictability to pseudo-randomness. This stage is, the second stage is very similar to the work of Eitner, Alcond, and Vadam, but since bits unpredictability is a simpler notion, then the proof is simpler and we get better parameters in the second stage. And along the way, we use simple tools like Goldreich-Levin and Chernoff. We don't need anything which is too complicated to teach. So let's start from the first part, how we construct bits unpredictability from one-way functions. So assume we have a one-way function f from n bits to n bits, and let me show you the construction. So we take M to be a random matrix, n by n matrix, and X a random string of length n. And I'm going to think about M as a function from n bits to n bits by just considering the matrix multiplication. So I'm going to think on the input as a vector of length n, and the function is the multiplication of X by M. Or in other words, the M of X is computing the Goldreich-Levin hardcore predicate between X to each one of the rows of the matrix M. And now the construction is the function gmx, a function which is parameterized by the matrix M, is just M of f of X and then M of X. So we are putting two n bits. And this distribution, of course, is not pseudo-random. If we know M, then we can, given M of X, compute X. With high probability M is an invertible matrix. We can compute X and compute M of f of X. So this distribution is not pseudo-random. But the question is, what happens if you read this distribution bit by bit in an online fashion? And the theorem says that for a predictor that knows M, this distribution has n plus log n bits unpredictability. So there are n plus log n bits that we cannot predict when we read it bit by bit. So how do we prove it? Let me start with a simpler task. I will start with proving that this is true for regular one-way functions. So a function f is regular or r-regular if every image has exactly 2 to the r pre-images. So every image has the same number of pre-images, which is exactly 2 to the r. And in this case, the claims is that roughly the n minus r first bits of M of f of X and the r plus log n first bits of M of X are unpredictable bits. We cannot predict those bits. And the proof is very similar to the proof to the construction of pseudo-random generators from regular one-way functions. Roughly speaking, if we are outputting only the green area in this scheme, only the unpredictable bits, we get something which is very close to a PRG. And the high-level intuition is that if f is a regular one-way function, then f of x for a random x is a uniform distribution over the sets of images, which is a set of size 2 to the n over 2 to the r. So it says I mean entropy. So we can use extractor or the leftover Ash lemma or Goldreich-Levin in order to extract roughly n minus r random bits from it. And m of f of x is exactly n minus r first bits of m of f of x is exactly the Goldreich-Levin outcome predicate. So the first n minus r bits of m of f of x are random. And then the last bit of m of f of x maybe are not pseudo-random. But when we finish to read m of f of x, even if we know f of x, still the distribution of x is a uniform distribution over all possible pre-images of the image. So it's as mean entropy at least r. So again, we can extract r bits of randomness from m of x. But moreover, because f is a one-way function, we can use Goldreich-Levin in order to extract additional log n bits. So the first r plus log n bits of m of x are also pseudo-random, and we cannot predict them. So this is the proof of the construction of bits unpredictability from regular one-way function. This distribution has n plus log n bits unpredictability if f is regular one-way function. What happens with arbitrary one-way function, which is not regular? So the idea is the same construction works. And the main observation here is that every function is a combination of regular functions. What do I mean by that? So we can define for every input x the local regularity of x, the log number of pre-images of f of x. And this is some number. If f is a regular function, that this number is the same for every input, is exactly equal to r. But in arbitrary function, this can be any number between 1 to n. But we can partition now the set of the possible inputs into n sets, such that the j set, dj, is the set of all x's such that the local regularity of x is equal to j. And the idea is that now, if we look on f restricted to this set, to dj, this function is a regular function. Now, if we use our construction of bits unpredictability from this function, we will get n plus log n bits unpredictability. And f is a combination of such regular functions. So when we use our construction on f, we get a convex combination of distribution with n plus log n bits unpredictability. And it turns out that such a convex combination is also a distribution with n plus log n bits unpredictability. So this is the construction from any one-way function. Now for the second stage, extracting from bits unpredictability pseudo-randomness, construction PRG. So we know how to construct bits unpredictability from one-way function, and we said that this distribution is not pseudo-random. We can find f of x given m of x. So we need to respect the next bit property. We need to use some extractor that uses this bit unpredictability structure. And we are going to use the simple and elegant construction of Eitner-Reinkondel-Vadan. So it's going to be the same construction. So the first step is to convert bits unpredictability to what we call random bits unpredictability. The problem is that in our original distribution, we don't know which bits are unpredictable. It may be the case that for some I, the ith bit is always predictable. And then we don't want to use it, but we don't know that it's always predictable. So we change the distribution to a distribution in which each bit has the same probability to be unpredictable. And the idea is just to take random shift. So we take n copies of our original distribution, and identical copies and independent copies, and we choose a random index I. We remove the first I bits of the first block and the last m minus I bits of the last block, and output what is in the middle. And now, since I is random, the distribution of each bit in what we output is the uniform distribution over bits in the block. And then the probability of each bit to be unpredictable is exactly the expected probability of a random bit to be unpredictable. So this is the first step. And the second step is the extraction. So now we take a distribution with random bits unpredictability. We take T copies from this distribution, put each copy in a row, and we apply on each column an hash function. And we use the leftover hash length. And the hash function is from T bits, when T is the number of copies we take. And it outputs S bits when S is roughly the expected number of unpredictable bits we expect to see in each one of the columns. And this process respects the next bit unpredictability. For each distribution, we extract randomness from each bit separately. And in this point, we improve the parameters over HRV because our notion of bits unpredictability is simple. So to conclude, we define the notion of bits unpredictability as a weaker notion of pseudo-entropy. And we gave a simple proof to the fact that we can construct pseudo-random generators from 1F functions with slightly better parameters. The construction is by constructing bits unpredictability from 1F functions and then converting bits unpredictability into pseudo-randomness. An interesting question is, of course, to simplify other proofs in cryptography. Thanks.
Thank you. We have time for maybe 2 questions. I have a rather vague comment than a question. Something about this reminds me of polar codes, where you have this, I think what they want to do is polarize the amount of entropy conditional on something. Maybe there's something.
Yeah. So it sounds very, very related. I didn't think about it, but it sounds very.
Anything? Yes.
Do you think that the matrix M is necessary to get bits unpredictability? Do you think that f of x comma x is also going to be bits unpredictable as it is like a next block pseudo-entropy?
So the one of the construction of pseudo-random generators use f of x as a generator of next bit pseudo-entropy. This distribution doesn't have bits unpredictability because maybe we can predict like f of x may be unbalanced distribution. So maybe we can, maybe the first bit of f of x is with probability 3/4 equal to 1. And then it's not entirely unpredictable. But it's as pseudo-entropy, and this was the original construction.
Thank you.
Okay, thank you. Let's take the rest offline. Let's thank Norm again. And the next talk also relates a couple of very fundamental concepts. It's about one-way functions and sparse languages by Yanyi Liu and Rafael Paz, and Yanyi is here to give the talk.
All right, thank you, Prashant, for the introduction. And today I'm very happy to be here to talk about my work on one functions and sparse languages. This is a joint work with Rafael Paz. So today we're going to focus on the notion of one functions. Proposed by Jiffy and Hammer in 1976. One function, well, it's just a function that's like easy to compute but hard to invert. And one function is really like the central object of in cryptography. And whether one function exists is, well, unequivocally the most important open problem. And because we know that one functions are both necessary and sufficient for private key encryption, pseudo-random generators, digital signatures, authentication schemes, pseudo-random functions, commutative schemes, and so on. And those primitives are often referred to as a private key primitives or mini-crypt, as they exclude the notable example of public key encryption. And they also don't include multi-party computation and obfuscation. In addition, as observed by Impagliazzo in 1995, the existence of one function is equivalent to, well, being able to sample hard instances together with the with its witness. So we might ask, well, how about just being able to sample hard instances? And however, this is arguably, like another biggest open problem in cryptography, which is to show that NP is hard on average implies the existence of one function. And today our focus is, well, getting one functions from average case hardness. And the question we're asking is, can we identify some simple properties of a language L and a distribution D, such that if L is hard on average with respect to the distribution D, implies the existence of one function? And somewhat surprisingly, today we're going to show that, well, if you take like a language that is sparse and a distribution that has high entropy, and they fit into our theorem, so like sparse languages, average case hardness of sparse languages gives the one functions. Okay, so let me introduce the notion of like sparsity and the notion of high entropy that we need. So recall that like a language is just like a subset of a 0, 1, 2 star. And we say that it's spar or it's like S spar if kind of on each slice of the language, meaning like a statement over of length n, it has at most S of n instances. So they have like a few true statements on every input length. And today we're going to focus on like the notion of sampleable distribution. A sample distribution is just like a distribution that can be generated by like an efficient algorithm. And we say that this distribution has entropy h if the standard entropy of the distribution on security parameter n is at least h of n for every n. And now we are ready to introduce the notion of a average case hardness that we rely on. So here we have like a hardness parameter alpha. So morally, the larger alpha is, the harder the language is. And we say that L is alpha hard on average with respect to the distribution D if no efficient machine H can decide the language L given like a random statement generated by D with probability at more than 1 minus alpha for infinite many n. So if alpha is 0, this is saying, oh, this is kind of worst case hard. And if alpha is like 1/2, this is saying nobody can do better than like a random guess. Okay, so this is the notion of average case hardness. And let me introduce our main theorem. So we show that the following 3 bullets are equivalent. So let me kind of explain what does it say. And so let's look at the implication that bullet 1 implies bullet 3. So this is saying that to deduce the existence of one function, we just need the existence of a sparse language L that is 1/2 minus 1/4 and hard on average with respect to D. So this is kind of distantly pretty hard, right? So this is saying no efficient machine can decide L with probability more than 1/2 plus 1/4 n. And in addition, the distribution D has to be of entropy, h of n, and the amount of entropy should be at least, say, the logarithm of the sparsity of the language plus like a little bit, like a 4 log n. So if we have like a sparse language that is 1/2 minus 1/4 and hard on average with respect to such a distribution, then we get one functions. And then in addition, if we look at the implication that 3 implies 2, this is saying that if one function exists, then we get like a language that is within NP, and it's like very, very kind of average case hard. It's like strongly average case hard, namely 1/2 minus negligible, and with a distribution D that has a lot of entropy. So the entropy gap here is like n/3 as opposed to 4 log n. So and then we can say we can see like 2 trivially implies 1. So this kind of concludes our this is kind of what our main theorem is saying. So yeah, as mentioned, like average case hardness of sparse languages with high entropy implies one function, and the converse is also true. And additionally, we get hardness within NP. And I want to highlight here that somewhat intriguingly, well, there's no computability requirements on the language L. So L could be, not even efficiently computable. or not even computable, or not even like recursively enumerable. And so is the sparsity threshold S. Well, like this is kind of very strange. And in addition, if you think about it, this opens up for the door of using probabilistic arguments to define like a hard on average language L. Say like we can probably like potentially use like a randomized restriction or techniques like that. And let me mention that in the paper we also showed like languages like KSAT and TClick, and the language of small Kolmogorov complexity strings. They are sparse and therefore they fit into our main theorem. And note that Ilango, Ren, and Stanfarne, they have already proved these implications, but they rely on the notion of a Kolmogorov complexity. And in some sense, we showed that the notion of Kolmogorov complexity was perhaps a mirage in their work, and sparsity is a central feature. Okay, so let me use the last 5 minutes to briefly explain how the proof goes, and to see that 3 implies 2, namely when functions gives average case hardness of a sparse language. We just need to consider like the PRG language, meaning like if the string is pseudo random, then this is a yes instance. If it's not is a uniform string, this is a no instance. And this language is like distantly pretty sparse. And if you consider the distribution that's like 1/2 PRG plus 1/2 uniform, is going to have a lot of entropy. And we basically conclude that this is a sparse language that is average case hard. And in addition, note that like 2 trivially implies 1. So our focus today would be to argue that the existence of a sparse language, average case hard sparse language, gives a one function. And let me briefly sketch the proof. It's actually quite simple. So we assume for contradiction that there is no one function. And our goal is to decide the language L with respect to the distribution D. And we know that if there's no one function, then approximate counting is possible. So meaning that given like a distribution D and a string X that's sampled from D, we can count how many random tapes there are that leads the distribution D to output my sample X. So we're going to use like this approximate counter to decide the language L. So how do we do? So our reduction on input like a string X of length n, we'll use the approximate counter to decide whether my input string is rare, meaning here we say that the string is rare if it samples by D with very, very small probability, namely smaller than 1/2 to the entropy. And if X is rare, we simply output no. And otherwise we output a random guess. So the reduction goes like, so if it takes a string and you check what's the probability that the distribution D generates my string. And if the probability is really small, meaning it appears like the string appears really rarely, and then we just say no, this is no instance. And otherwise, if it's like a common, then we say we output like a random guess. Okay, so let me give you like a quick analysis of this reduction. So think about conditions on the events rare, meaning that if your input string is like rare, you can see that we fail with only probability 1/n², very small probability. So this is because if the input string is like rare, and there are just this many like yes instances, so meaning like most of the like real strings, we're going to be like a no instance, and we're going to only fail with probability like 1/n², very small. And in addition, the event rare happens with probability at least 1/n, due to the distribution having high entropy. So because it's like a high entropy distribution, so it has to sample like many like rare strings, and therefore we can conclude that so combining these 2 points, right? So if this is a rare string, then I'm basically going to output the correct answer except for very small probability. And if this is a common string, then I toss a random coin and I don't lose too much. So by combining, in addition, real happens with probability 1/n. So our algorithm will succeed with probability at least say 1/2 plus 1/n, which kind of concludes our analysis. So this is basically the proof. And to conclude, today we have seen that average case hardness of sparse languages with respect to high entropy distributions implies the existence of one function. And my talk ends here. Thank you for listening.
Yeah, thanks, Yanyi. We have time for a couple of questions.
Yes. Can you repeat your question? Like, what's the goal?
Do you have a mic?
Do you hear me?
Yes.
Why can't you instantiate assumption 1 with a random language, which is what you suggested?
Why can't we
Yes.
instantiate with a random language? So I want to know, like, what's the kind of the goal of your arguments? You want to say construct one function like unconditional?
No, why can't you prove that one holds unconditionally for just a random set of strings?
Like which holds like for a random set of strings?
Your assumption one. So your assumption one said that if I have a language that is concentrate, that is I don't know, is sparse and is hard on average for some distribution D, then I can get a one-way function out of that.
I think you need an efficient sampler, Andre.
Huh? You need an efficient sampler for D? Okay.
Yeah, you need like a so
there is an assumption
we're
on D.
going to focus like we focus on like sample distribution.
Okay.
So you have to have like an efficient sampleable distribution. Thanks for the question.
Okay, we can take one more question while maybe you can set up the next speaker. Okay, if not, let's thank Yanyi again. Okay, the next talk is going to be online. It is about security proofs for certain kinds of key alternating ciphers in an idealized model. It's by Lixing Yu, Yusai Wu, Yu, Jinfu Sao, and Xiaolei Dong. The talk will be given by Yusai Wu as soon as they appear on the screen.
Okay, thanks for the introduction.
One second, I can't see your slides yet. Yes, you're good.
Can you see me sharing?
Yes, please go ahead.
Oh, okay. Thanks for the introduction. Due to visa issues, I can't attend this conference live in Taipei, which is a pity for me. So I will give my talk online. Well, let's get started. Hi, good morning. Welcome to my presentation on security proofs for key alternating ciphers with non-independent random permutations. This is a joint work with Lixing, Yu, Zhengfu, and Xiaolei. Let's first see the definition of key alternating ciphers. CAC is very simple, just alternately XORing one round key and invoking one round permutation. Each string in the figure has the same length denoted by n bit. It provides a general framework for constructing block ciphers such as AES. In T-round CAC, also round keys and permutations are independent and random. In symmetric cryptography, provable security is often to show that if the components are secure, then the construction is also somewhat secure. Then in practice, we just need to design secure components for instead. This work focuses on the random permutation model, which will be defined later. For T-round CAC, The well-known result shows that if the round keys and permutations are perfectly secure, then the T-round CAC is also almost perfectly secure up to the 2 to the Tn of T+1 queries. Note here that the proof is information theoretic and not by reductions, and the result does not rely on any unproved hypothesis. Because the two assumptions are quite strong, a natural question is whether the assumptions can be weakened. Referring to the practical ciphers, such as AES, the dream version of T-round CAC is that all the round keys are generated from a short string, and all the round permutations are the same. This work achieves the second minimization. More generally, we also consider the CAC type constructions, where the round keys are independent and random, and the round permutations are non-independent. This means that the same round permutation can be used in different rounds. What we're most interested is the CAC with a single permutation, named KCSP. As we can see, all the round permutations in KCSP are the same. This work focuses on the random permutation model, where the distinguisher aims to distinguish CAC from a truly random permutation named P0. Additionally, the distinguisher also has the black box access to the underlying permutations. Therefore, the distinguisher D faces T+1 oracles in either world. The only difference is that the construction oracle CAC in real world depends on the other T primitive oracles, while the construction oracle P0 in ideal world is independent of the other T primitive oracles. Similarly, in T-round KCSP, the distinguisher D only faces two oracles in either world. We now review the known security bounds of CAC and KCSP. The measurement here is the query complexity, because the adversary is computationally unbounded. In previous work, the proof of KCSP is much more difficult than that of CAC, and there's no security proof for KCSP with 4 or more rounds. This work addresses this problem, and its proof is not as difficult as previously thought. The main contribution of our work is to prove that T-round KCSP is secure up to the 2 to the Tn of T+1 queries for all T. In other words, the T-round KCSP and the T-round CAC essentially have the same security level. What does it mean? It is known that practical ciphers such as AES often use the same round permutation. Now we can see that this design philosophy is theoretically sound. Compared to previous work on 3-round KCSP, our proof is significantly simpler, and the security bound is more accurate. In particular, we propose general proof techniques for constructions with non-dependent round permutations. As byproducts, we are also able to prove a tight security bound for any T-round CAC type construction. Now we outline the proofs at a high level. First of all, the interaction between the distinguisher and oracles can be recorded as a transcript, which includes all information that the distinguisher can know. Any transcript consists of 4 tuples, and each tuple corresponds to a query and its response. We use T-real to denote the transcript distribution in real world, and use T-ideal to denote the distribution in ideal world. We follow the graph view used in CS14 to represent transcripts. In brief, if we know that pi of u is equal to v, then we draw a pi edge from u to v. At a high level, the proof uses the well-known edge coefficient technique, which turns the main task of security proof into bounding combinatorial probabilities. The main challenge is to lower bound this ratio for any good transcript. Typically, the difficult part is the probability in real world. Our techniques focus on lower bounding this probability, which is essentially a complex combinatorial problem. We start by illustrating a transcript for 3-round CAC in graph view. In this figure, the green parts, the green highlights, are the ones fixed by the transcript, whereas the Q1, Q2, Q3 represent the primitive queries, and the Q0 represents the construction queries. The key probability to bound is defined as the P of tau. Its intuitive explanation is that each starting point xi ends exactly at the corresponding destination yi, and this probability is over the pi's highlighted in yellow. They are truly random permutations compatible with QIs. This is essentially a general counting problem. What we really need is a good lower bound, and we will use constructive methods to get there. Now let's see what happens when we move to KCSP. The change is that all the random permutations and the random primitive queries are identical here. Thus, the probability P of tau is over the only one truly random permutation, P1. The nature of identical random permutations introduces additional difficulties. First, each new edge affects all rounds. For example, if we define that P1 of U is equal to V, then this edge will be added to each round graph. Second, one edge can be reused in different rounds. For example, as we can see, an edge can be reused twice in the same path. Or an edge can be reused twice in two different paths. Moreover, there is no limit to the number of times an edge can be reused. All of this makes the counting extremely complicated. Fortunately, what we need is a lower bound, so our solution is to use carefully designed methods to construct paths, and then count them. Next, we outline some key ideas in the proofs. The first is a general transformation, that can significantly simplify the proofs. In a good transcript, there may be different types of pairs xi, yi, and this transformation allows us to consider only one type. In particular, this transformation works for all CAC and CAC type constructions. For example, in 3-round KCSP, there are 6 possible types. We let each of the first 6 pairs to illustrate one type. Our transformation is to replace all pairs of the first 5 types with type 6 pairs and leave the set Q1 unchanged. In other words, the set of paths to be connected becomes Q0 hat. However, this direct transformation alone is not enough. We should additionally require the replaced pairs to be connected in the most wasteful way. The meaning of the most wasteful way is literal. That is, we always use new edges to connect paths, and each new edge cannot be reused. We can prove that the probability that all the paths are connected becomes smaller after the transformation. Therefore, our task shifts to finding a good enough lower bound for the new probability p hat of tau. In contrast, without this transformation, we need to handle about t-squared cases for a t-rounded construction. But now, we only need to deal with one case for any t. To lower bound the target probability p hat of tau, we partition the sample space according to the number of new edges used to complete the Q paths. The size of each set Si can be determined by a concept named core, which represents the set of edges used in the Q paths. Therefore, we will construct the cores explicitly using well-designed methods, and then sum up all their cardinalities. Obviously, the constructed green part must be a lower bound of the sample space. Nonetheless, we should point out that obtaining a good enough lower bound is challenging and involves many technicalities. Please refer to the full version on ePrint for more details. You can also find us via email. Any questions are very welcome. Finally, we conclude this talk by providing more insights from proofs. Because our proof is constructive, we actually sketch a rough picture of the sample space. In particular, the proportion of the most full way decreases as the dependence of random permutations increases. Second, the vast majority of reused edges are used exactly twice. Furthermore, in addition to the CAC and CAC type constructions, we believe that using our general techniques, the security proofs for other constructions with non-dependent permutations should also no longer be a problem. Okay, that's all for this sharing. Thank you all for your attention.
Thanks a lot, Yosai. Do we have any questions while Alon sets up? If not, let's thank Yosai again.
Okay. Thank you all.
The next talk is about constructing public key encryption from some interesting new combinatorial assumptions. It's by Andrei Bogdanov, Pravesh Kothari, and Alon Rosen. And Alon is giving the talk.
Thank you, Prashant. Can you hear me? Is the pointer working? Good. Hi, everybody. This is joint work with Andrei Bogdanov and Pravesh Kothari. Works. Okay. So the work is about searching new public key encryptions. I will not say it's a more important open problem than proving the existence of one-way functions, but I think it is. So it's just because it's more challenging, and one-way functions we could find heuristically more easily plausible candidates, whereas for public key encryption it's much harder. So we do think it's an important problem, and following the footsteps of Applebaum, Barak, and Vigdezon, who tried already over a decade ago to come up with the alternative candidates, will re-examine the question with constructions that are related to their constructions. They gave, I wrote 3, but I think it's actually 2 constructions in 2010 based on 3 assumptions. The assumptions are different in nature, and I will give you an idea of what kind of assumptions we want to rely on. So in this work, we give a new candidate public key encryption that is ABW-like.
It has a quasi-polynomial security. It's not very secure, but it is still, we think, interesting. And one interesting and prominent feature of this candidate is that we guide the design and the justification of its security using the so-called low degree method, which is a sort of a heuristic leap of faith for arguing indistinguishability of distributions. Traditionally, this comes from the field of hypothesis testing. And more generally, we think it's an interesting direction to try and tie cryptography to the field of statistical inference. I hope I'll have time in the end of the talk to talk about it a bit. Okay, so how does the candidate public key encryption look like? And this is the blueprint that is also followed by Appelbaum, Bach, and Vigdorson at a high level. So the public key is a pseudorandom generator that takes n bits to m bits. This is too much. Encryptions of 0 are just pseudo-random strings. You pick a random X and map it to a pseudo-random string. And encryptions of 1 are just random strings. So indistinguishability of ciphertext follows from pseudo-randomness directly. And then you need to specify how to decrypt. And you do this by planting some structure in the description of the pseudo-random generator that enables you, the planter, to distinguish between a random and the pseudo-random. And the challenge will be to find ways how to plant the trapdoor in H so that the pseudo-random generator remains a pseudo-random generator so that nobody else besides the planter can distinguish. So we call the description of this pseudo-random generator H. As you see, we'll see later in our case, it will be a hypergraph. And there are two ways to conceivably plant this secret information. One is statistical. So you plant the secret information in a way that is statistically indistinguishable from a random object H. And the other one is computational. ABW's public key encryption schemes, one planted statistically, one planted computationally. And also in this work, we plant in a way that is computationally indistinguishable from random. What you get in other cases is that the distribution, when you use a planted H versus a random H, is that it's indistinguishable from the random Y, and hence you get computationally indistinguishability of encryptions of 0 from encryptions of 1. So the pseudo-random generator that we are going to consider is a very simple one. It's a Goldra's function. It has n bits of inputs at the bottom and m bits of output at the top. And the construction is specified by this bipartite graph or a hypergraph. In our case, the degree of the hypergraph will be 5. 3 out of the 5 bits of every output incoming, every output bit will be used to XOR the corresponding input bits, and the 2 other bits will be used to AND the remaining 2 bits and XOR to them. So this is the predicate. And we'll try again with this. So you have 5 bits of input. You XOR 3 of them, and then you XOR the result with the AND of 2 bits. You can think of the XOR of the 3 bits as the linear part and the AND as the noise part of the linear part. We will now, in this short talk, focus only on the linear part. One thing to notice is that there's a limit to how much the output length can be longer than the input length. In particular, when n is the input length and m is the output length, then when m is roughly n to the 3/2, this generator is not pseudo-random. And the reason is the following. You view the output of the generator as noisy linear equations, as we just specified. When m equal 3/2 is the square root of n choose 3, that's where it comes from. You have collisions by the birthday bound, meaning that you have repetitions of the linear part, which means that you can XOR the bits where you have this collision and cancel out the linear part. And now you have XOR of 2 ends, and this is a 1/4 bias bit, which can be used to distinguish random from pseudo-random. More generally, you could think of, instead of collisions of 2 elements, you could think of longer linear cancellation, length L cancellation, essentially things that XOR to 0, like a length L subset of bits that XOR to 0. And again, if you allow for longer dependencies, they're more likely to exist. If they're too long, the bias will be too small. You will not get the distinguishing probability. So what you want is you want to find this middle ground where the dependencies are not too short, but not too long, and they abound. And the dependencies that we consider in this work are logarithmically long. And this is what we'll use for the public key encryption scheme. It looks like this. This is a linear algebraic way of viewing the entire H, distribution H. Think of it as operations mod 2. So you have a matrix with n columns. This is the corresponds to the input size of the pseudo-random generator, and m rows. This corresponds to the output size of the pseudo-random generator. Each row has exactly 3 ones. These are the bits that are selected to be XORed in each one of the m output bits. And now you want to examine at what length you get linear dependencies. Clearly, if you allow linear dependencies of length n plus 1, you will get for sure a linear dependencies because you have n columns. Also notice that since the rows, each row is chosen at random, it has very low weight. It has weight 3, then with noticeable probability, you'll get a collision just by virtue of the low number of possibilities for each of these rows. But what we will be interested in the existence of many such collisions, and these are not guaranteed in this setting of parameters where you just go below the birthday bound, just a bit below the birthday bound. So the probability here is just 1 over poly n, and you expect a small number of collisions. There is a remarkable theorem that emerged in the context of random 3-SAT by Feige, Kim, and Ofek that shows that with the probability almost 1, you get exponentially many short dependencies of a sublinear length, n to the 2 delta, where delta is how much you are below n to the 1.5. But this is too long for us because the bias that you get from this kind of dependencies is too small. It's exponentially small. So this is why in particular I focus on logarithmic dependencies. And the problem with logarithmic dependencies is that we do not expect it to abound too much for these parameters. So what we do, we plant these dependencies in the graph with the hope that it's computationally hard to detect them. And our reasoning is based on the low degree method where we used to justify this indistinguishability. So how does it look like? The object we're talking about is a subset of the rows. It's like a sub-hypergraph of this hypergraph with m edges. The object, we call it a hyperloop, but it's just a fancy name for a short linear dependency mode 2. And what do you need for a short linear dependency mode 2? You need that every column has an even number of ones. So then if you XOR all the rows in this subset, you get a 0, the all 0 vector, mode 2. So in short, a length L hyperloop is a length L linear dependency. How does a hyperloop look as a bipartite graph? It looks like this. You can see that in this case, every input node doesn't only have even the out degree, but it says, in fact, out degree 2. So this is a very strong kind of hyperloop. And we have 9 nodes. This is how a planted hyperloop looks like visually. In our construction, we plant n to the epsilon identical hyperloops. So we fix a hyperloop, the one that you saw, or something related to the one that you saw. You know that this is the hyperloop that we're going to be planting. And we challenge you to find the planted hyperloop when they sample the planted distribution accordingly. So the conjecture is that the planting is computationally indistinguishable against quasi-polynomial adversaries. It's sufficient for security, not clear that it's necessary. Maybe the construction is secure even if the planting is distinguishable. It's just that using this, we can elegantly argue security of the encryption scheme. As I mentioned, the two distributions planted and not planted are not statistically close for the reason that I mentioned. One last thing I want to mention is this low degree method, which is something relatively new to the cryptography community, I think. And essentially can be summarized in this sentence. If you have two distributions that cannot be distinguished by no degree D polynomial, no low degree polynomial, then no adversary or no distinguisher that runs in time n choose D can distinguish between the two distribution. If you take t to be logarithmic, for instance, you get indistinguishability against quasi-polynomial time distinguishers. Empirically, in the hypothesis testing community, and this corresponds to the best known algorithms for distinguishing these kind of planted distributions. I have to warn you, it's not a sound model. It does not model algebraic attacks, so it's not like an unconditional proof of security. But it can be, and it has been in our case, a useful guide on how to plant. I'm going to skip this slide because I think I'm short of time. I just want to show you a specific hyperloop that one could consider. So, and the criterion that we were guided to by considering a low degree indistinguishability. So what you see on the right is just a dual view of the graph on the left. Since each vertex here has degree 2, you can view it as an edge here. And then you can view the vertices as edges. So these two objects are just different representation of the same graph. And the regular graph on the right, the property that we need from it is that it's a small set expanding. And once you guarantee that the graph on the right is small set expanding, and you plant it, it falls out from our theorem that the distributions are low degree indistinguishable. And the nice thing is that we're planting very small objects, logarithmic size objects, so we can exhaustively search in an automated way and test whether the graph that we're planting is small set expanding by just going over all possibilities. Since it's such small object, here's another object that we found on 14 vertices, and we certify that it's small set expanding, and then we can claim the following quantitative claim. No degree 1 minus epsilon d distinguisher can detect this L0 equals 14 vertex hyperloop with constant advantage as long as the number of output bits in the generator is less than 3/2 minus 1/8. This is an unconditional statement given an epsilon. Okay, how much time do I have, Prashant? A minute. So I'll stop here for questions.
Thank you, Alon. Any questions? I have a question. The end to the 3/2 bound came because you said there will be collisions beyond that, right? But what if you sampled without replacement?
Then there will be no collisions, but I don't. Ander, do you know what will happen to the pseudo-randomness? Other attacks. Okay.
Okay, I'll ask you more later. The next speaker can please set up, please. Thanks again, Alon. The next talk is about, again, assuming certain other interesting combinatorial assumptions about planted subgraphs to do sort of very different things, actually, different interesting things. The work is by Damiano Abram, Amos Bemel, Yuval Ishai, Eyal Kushilevitz, and Varun Narayanan, and Damiano is giving the talk.
Everybody, thank you for the introduction. Now I'm going to talk about this work in which we studied a new application of planted graph assumptions in cryptography. And we mainly focus on two topics, namely private simultaneous messages protocols and secret sharing. So I would say the main application, the main contribution of our work is the introduction of two new assumptions that we called planted subgraph and planted random subgraph. From the first family of these assumptions, we managed to build private simultaneous messages protocols with public information, and I will explain later what this means. And yeah, these protocols allow to securely evaluate the function f with domain n times n, with messages that are logarithmic in n from the parties. From the second family of assumptions, instead, we managed to build a forbidden graph secret sharing scheme with public information. And that means essentially that when we secret share a bit, we not only provide shares to the parties, but also some public information that is needed during the reconstruction phase. And yeah, this scheme has a share size that is logarithmic in the number of parties. Next, we studied what is possible in the context of secret sharing with public information and computational security. And we, in particular, found some lower bounds one for generic access structures and one for 2 out of n secret sharing. And finally, we focused some more on this last topic, and we asked if it is actually possible to obtain 2 out of n secret sharing schemes with public information that are better actually than Shamir, meaning that the share size is now 1 minus delta times log n, so where delta is some positive constant. And yeah, we couldn't really answer this question, but we reformulated it in an equivalent way, usually using a planted graph problem that can be interesting beyond the topics of this presentation. Okay, so let's start by explaining what planted graph problems are. So for planting, we deal with 2 distributions. The first one is called D8, and it's the distribution of the hidden graph. This is a graph with n nodes, and yeah, the distribution can be arbitrary. For instance, it can be our favorite distribution for this presentation, that is the octopus graph, and yeah, ignore that it's just a cycle. Then there is a second distribution called DA, that is the distribution of the ambient graph. This is a graph that is larger. It has capital N nodes. And yeah, in all the application we will see today, the ambient graph distribution is uniformly random. So it is graphs like the one you see on the slide. Now, what does it mean planting? So our goal is to plant a copy of the hidden graph in the ambient graph. And we do this by sampling lowercase n random nodes of the ambient graph. And we connect them with an edge if and only if the corresponding 2 nodes in the hidden graph are adjacent in the hidden graph. Okay, given these 2 distributions, we can consider a decision problem in which the adversary is provided with a hidden graph coming from the distribution D8, and a larger graph that is obtained by an ambient graph by either planting the hidden graph or not doing it. And what we argue is that for some distribution DA and D8, this problem is actually hard. There is another variance of these assumptions that we call planted graph with hints. And here, essentially, we provide some leakage to the adversary. In particular, we specify where a subset of the nodes of the hidden graphs are planted. For instance, we can reveal where the head of the octopus is. And yeah, the adversary now will be given either with a large ambient graph that contains the whole octopus and we leak where the head is, or we just provide a graph that contains only the head and nothing else. And yeah, again, we argue that for some distribution DA and D8, this decision problem is hard. So of course, like planted graph assumptions are a quite large family. So it depends a lot on this distribution D8 and DA. So in the paper, we consider several applications, several instantiations. And yeah, probably the most popular is the planted click assumption, which is well studied. We know it since the 90s, and I would say that it's generally a well-studied problem. And yeah, in this setting, the distribution D8 of the hidden graph is deterministic, and actually it outputs a node click, and the ambient graph is uniformly random. In this work, we introduced 2 new variants of these planted graph problems. The first one is the planted subgraph problem. The second one is the planted random subgraph problem. In both cases, the ambient graph will be random as for planted clicks. What changes are instead the distribution of the hidden graphs. For planted subgraph, as for planted clique, the distribution is deterministic. But instead of planting a clique, we planted any graph you want. For instance, the octopus graph. For planted random graph, instead, the hidden graph is a random lowercase n node graph. And yeah, what we conjecture is actually that the hardness of these problems increases if we go from the left to the right of the slide. So essentially what I'm saying is the clique is the easiest subgraph we can detect. And the idea behind this is that cliques are very symmetrical objects that are extremely dense, whereas a generic subgraph don't have these properties. So we can leverage the symmetry of cliques to detect them. And our conjecture is actually supported by some low degree analysis that we perform on the problem. And yeah, Alon explained earlier what it is. Okay, what about parameters? How big should the ambient graph be in order to hide the planted subgraph? For planted clique problem, this is a well-known fact that the ambient graph should be at least n to the 2 plus delta, where delta is some positive constant. For a planted subgraph, I mean, we believe that this problem is harder to solve. So we conjecture that for an overwhelming fraction of all planted subgraph, it is sufficient to have ambient graph of size n to the 1 plus delta. So notice 2 plus delta on the left, 1 plus delta on the right. And yeah, this would imply that for a planted random subgraph, n to the 1 plus delta is sufficient. There is, however, a caveat, and the caveat is that these decision problems hold only against quasi-polynomial time adversaries. And the distinguishing advantage is not negligible, but actually it's inverse polynomial. And these two properties will actually be inherited by all our applications. And yeah, there is a way to fix them, for instance, with the advantage using the Yao XOR lemma in some cases, but yeah, it has a little cost in the increasing the share size. But yeah, there is also good news. We believe that this assumption hold even if we provide hints, as long as these are constant in number. So in our application, the number of leaked nodes will be exactly 2. Okay, for the rest of the talk, I want to focus on our private simultaneous message protocol. And I will start by explaining what this public information means. So suppose that we have a function f with domain n times n and output in just a bit. And we have 3 parties, Alice, Bob, and Carol, where Alice and Bob hold some inputs x and y in between 0 and n. And they want to provide Carol with the valuation of f on x and y without leaking any additional information. So in a private simultaneous message protocol with public information, we rely on a setup. This setup provides Alice and Bob with some correlated randomness S0 and S1, plus some public information that is given to Carol or also the 3 parties. And yeah, this is the novelty. So in standard PSM, without public information, there is no I. After this setup, Alice and Bob will encode their inputs using the correlated randomness. And from that, Carol reconstructs the output in a secure way without learning anything else. So now I want to explain how we build our PSM protocol by using an example. Suppose that the function f just outputs 1 if x is equal to y or y is equal to x plus 1 modulo n. We represent this function f as a bipartite graph. So one side is for Alice, and there will be n nodes, 1 for each of her inputs, possible inputs. And the other side is for Bob, and again, there are n nodes, 1 for each possible inputs. And yeah, we connect each pair of nodes if and only if the evaluation of the function on the corresponding inputs gives 1. Now, this is actually isomorphic to the octopus graph, so we can represent it in this way. And yeah, our setup in the PSM protocol will just plant this graph into a larger ambient graph, and this will consist of the public information. The correlated randomness S0 and S1 will be instead the position of the blue nodes for Alice, so those corresponding to her inputs, and the position of the red nodes for Bob, again, those corresponding to the inputs of Bob. So now the question is, how do we perform the evaluation of the function? Well, Alice and Bob just need to take their input. They consider the node that the position of the node that encodes such input, and we'll just communicate it to Carol. So just to give an example, if Alice and Bob have inputs 3 and 3, so the evaluation should lead to 1. Alice will send the blue node on the left, which encodes 3. Bob will send the red node on the right. And yeah, now if we switch to Carol's perspective, what she will see is the following: this large random looking graph with 2 nodes. These 2 nodes are connected. So it will know that the output of the function is actually 1 because, I mean, these are 2 nodes of the subgraph that are connected. So it must be that the output is 1. However, Carol doesn't know which edge of the octopus it is given. So it will learn nothing else. Okay, and yeah, the message size M0 and M1 is logarithmic in N, so it's easy to check. Okay, this is the end of the talk, and here there is a slide with a summary of the results. And yeah, I want to point out an open question, namely whether there exists a better way of planting so that we have either a negligible advantage or security against sub-exponential time adversaries. And yeah, that's it.
Thanks, Damiano. Do we have any questions? I have a couple of questions while the next speaker sets up about the assumptions. The lower bounds on the low degree method you show, is that also with the hints?
Yeah, also with the hints.
Okay.
As long as they are constant in number. Yeah.
Okay. And the other question is for let's take the planted clique problem, right? Are there other families of algorithms for which people have shown lower bounds for it?
Like, maybe I didn't understand what you mean.
For the planted clique problem,
Yeah.
we have lower bounds on low degree algorithms.
Yeah.
Do we also have lower bound, for example, on lattice algorithms or something like that?
With the low degree method, I don't think
Outside
so.
of the low degree method.
I don't know.
Okay, thank you.
Sorry.
Yeah, thanks again, Damiano. The last talk of the session is on constructing batch verification protocols with some helper oracles. The work is by Amit Agarwal, Naveed Alamati, Dakshita Khurana, Srinivasan Raguraman, and Peter Rindal, and the talk is being given by Amit.
Hi. So today I would like to talk about my work on Blackbox verifiable computation, and this is joint work with my co-authors Naveed Alamati, Dakshita Khurana, Srinivasan Raguraman, and Peter Rindal. So let me start by first describing the problem. So here we have a client, and think of this client as a weak device, which has a batch of n inputs, x1 up till xn, and it would like to outsource the computation of function f belonging to some class capital F to a much powerful server. And the server is holding some code or circuit for which is implementing the function f. So after this interaction, the client would like to output n values, y1 up till yn, which are supposedly the function evaluated on the n batch of n x1. And as usual, we require completeness, which says that if the server is honest, then the client values that the values that the client outputs, y1 up till yn, is equal to the function evaluated on the n inputs. If the soundness, which says that if the server is malicious, then either the client outputs the right values or it aborts with high probability. Third, efficient verification, which says that the client's running time should be better than just recomputing the function from scratch on all the inputs. More formally, it should be sublinear in n times T of f, where T of f is the time complexity of computing f. So together, these three requirements are standard in any verifiable outsourcing scheme. The fourth property that we introduced new in this work is called black box verification. This, at a high level, it says that the client's protocol should be oblivious of the exact circuit or the code or the implementation for the function f that the server is using. And this is motivated by natural use cases. So for example, imagine, let's say f is just matrix multiplication function, and the server is providing some cloud computing service for implementing this function. The client might not be willing to go through the burden of auditing the implementation of the code or the circuit for the function that the server is implementing. Also, it might be possible that the server is just making frequent code updates to its implementation for the function, in which case the client would not like to redo the process of auditing. And it might also be the case that the code or the circuit for the function C sub f is proprietary, and the server doesn't want to disclose it to the client. So in the next slide, we'll model this black box verification more formally. So here is the setting, and the way we model it is the following. So we allow clients some access to some oracles. So the first oracle is this function oracle, which basically takes as input some value and outputs f applied to that input. Along with this, we also allow the client access to some helper oracles. Each helper oracle, ith helper oracle, is implementing the function g sub I. And think of these as some low complexity oracles, low complexity compared to the function f. Looking ahead, we will allow the client to make some small number of queries to this function oracle and some large number of queries to this low complexity helper oracles, in a way so that we still have efficient verification. And we call this model as oracle-aided batch verification in the paper, OWFs for short. So for non-triviality, we require that these helper oracles are less complicated than the function oracle. So formally, the time complexity of these helper oracles should be less than the function oracle. And for efficient verification, we put the following constraints. So we say that the number of oracle queries that the client makes to this function oracle should be some order lambda, where lambda is some security parameter. Note that lambda here is just independent of n. N can be, let's say, 1 million, lambda would be like 128. And then we also say that the number of oracle queries that client makes to these helper oracles can be as large as n times lambda, order n times. Along with this, the running time of the client should be sublinear in n times T of f multiplied with some poly lambda. And if you put these three constraints together, it basically captures the fact that the total workload on the verifier side, meaning the work done by the oracles plus the work done by the verifier, is sublinear in n times T of f. So as a positive result, we show the following, that if you assume homomorphic encryption, then there exists a black box verifiable computation scheme for this class of random self-reducible functions, which I will explain later. And at a very high level, we use this random self-reducibility property to achieve this notion of black box verification in a way which is inspired from prior work on program testing and correction. Along with this, we put in a kind of cut and choose check along with homomorphic encryption and RSR to get efficient verification while retaining soundness. So in the next slide, I will describe how our protocol looks like for the special case before going into that, let me first give you some background on what random self-reducibility is. So let's say we have a function f, and this function is said to have k RSR, where k is some constant, depending on the function. If it has these two algorithms, RSR encode and RSR decode. So what RSR encode does is it takes as input some value x in the domain of the function, and it splits it up into k pieces, u1 up till uk, where each piece individually is uniformly random. Now, if you apply f to these individual pieces, you get some values v1 up till vk. And then RSR decode can take in these values and output some value y, which equals f of x. The property that we have here is that RSR encode and decode procedures are much simpler than the function f itself. More formally, their time complexities are much smaller than the time complexity of computing. And there are different examples of RSR functions depending on different values of k. So in this slide now, I'll show you a basic protocol for functions which have KRSR where k equals 1. So imagine we have this function f which has KRSR where k equals exactly 1. And the client wishes to outsource the computation of x1 up till xn on this function f to the server. So as a first step, we allow the client access to this function oracle as was prescribed in our model, along with the helper oracles, which are precisely RSR encode and decode. So as a first step, what client does is it takes these n inputs, x1 up till xn, and forms this matrix of n cross lambda, where the ith column in this matrix is formed by invoking the RSR encode procedure on the ith input x sub I, independently lambda many times. So the client does this for all the n inputs and gets this matrix n cross lambda matrix. Then, so first note that each value in this matrix is uniformly random and independent from everything else. Now the client shuffles this matrix, and we call this M, and sends this shuffled matrix to the server. The algorithm on the server side is very simple. It just needs to apply its circuit individually to each entry of M to obtain a new matrix M prime. So it just evaluates the function on each entry of the matrix M, and then sends over this M prime to the client. Now client, as a first step, reverse shuffles this matrix M prime that it receives from the server. And as I mentioned before, it does a kind of cut and choose check on this matrix N. Now let me elaborate what this cut and choose check is. So think of N as this capital N as this N cross lambda matrix of V values, V sub ij values. So the client selects some subset of these entries from this matrix circled in red. And for each circled entry, it checks whether the value inside that entry, which is V, equals to F applied to the same, the U value at the same location in the original matrix that it formed. So, and exactly here is the place where it invokes this function oracle, because it needs to compute the function F for this check. And if this check passes for all these circled entries, the guarantee that we get is the following. We get a guarantee that all columns in N have majority correct values with high probability. Once we have this guarantee, the client can apply RSR decode procedure on each cell of this matrix N, and then perform a majority decoding on each column corresponding to ith input to get the Y values. Okay, so just a high level intuition on why soundness holds. So completeness holds directly from the correctness property of RSR. Soundness holds because of the following reason. So suppose you're dealing with a malicious server. The malicious server, when it computes the circuit C sub F on each entry of the matrix, it can do two kinds of attacks. Either it can corrupt too many entries in this matrix M prime, in which case it will get caught in the cut and choose check. Or the second kind of attack is that it corrupts only a very few entries in the matrix. Now, if it corrupts very few matrix in the matrix M prime, then because the entries are uniformly distributed because of RSR, we can argue that the corruption patterns would be distributed uniformly across all the columns. And in that case, the client can error correct these corruptions by applying the RSR decode and the majority decoding. So some observations. So note that the client-side verification here is completely oblivious of the circuit that the server is using. It doesn't depend on the circuit at all. This is in contrast with known snap techniques, which require the client and server to agree on some fixed circuit for F before entering the verification procedure. And hence, they are not black box. We also show that the size of the cut and choose check can be as small as log square lambda, where lambda is some security parameter. And this suffices to get a negligible soundness error. Let's also look at what the efficiency is on the verifier side. So in the protocol, the verifier only needs to make log square lambda queries to the function oracle, n times lambda queries to the helper oracles, which are RSR encode and decode, and order n times lambda local computation, which is because of the shuffling and the majority decoding steps. Now, let me give you an intuition on how we extend it to k RSR functions where k is greater than 1. So we show the case for k equals 1. So the main challenge here is that the outputs of RSR encode procedure are not jointly random. Although they are individually random, jointly they are not. And what happens is that if you run the protocol exactly as I described, the malicious prover can try to figure out which U values are originating from which particular input values X. And then it can selectively corrupt those values and avoid getting caught in the cut and choose step. The solution here is that we encrypt each U value under a fresh public key and send these shuffled encrypted U values to the server. Now, in order for the prover to apply F on this encrypted values, we need the encryption scheme to be homomorphic. And here is where we need the assumption of homomorphic encryption. And then after that, the verifier, after receiving the responses from the server, can locally decrypt and perform the cut and choose check as before. And the soundness proof for this protocol also turns out to be slightly non-trivial. In the paper, we need to formalize a kind of no signaling guarantee in order to show the formal proof. Now, in the paper, we also have an impossibility result. So a wishful aim for the impossibility result would be to tightly characterize the functions which admit such kind of black box verification scheme and those that do not. We do not manage to do so because there can be arbitrary properties of the function apart from RSR that you can possibly leverage in order to get such a black box verification scheme. So the weaker aim that we aim for is that we show that a large enough function class cannot have such a OBVC scheme. And the function class that we consider is basically the class of all functions from lambda bit input to lambda bit output. And we show that this class does not admit this kind of black box verification scheme. And the proof techniques turns out to be non-trivial because in our model, the helper oracles can contain arbitrary information about the function f in this class. And to properly formalize the impossibility result, we rely on some results from prior work from Coretti et al. And this is some work on how you handle non-uniformity and random oracles to formalize this impossibility proof. Thanks.
Thank you, Robert. Do you have any questions for Amit? Yes.
So first question is what's the advantage of using KRSR in your case for K greater than 1? Because apparently it introduces complications because of the fully homomorphic encryption. And the second thing is that, do you know any known impossibility results about the existence of KRSR where chi is arbitrary and large because it would lead to natural advances in secret sharing?
Okay, so to answer the first question, we do not deliberately try to deal with k greater than 1. It's just that there are functions which do not have k equals 1. The k equals 1 class is very limited. So for k greater than 1, we have much more examples of functions. And I'm not very sure of what was the second question. Can you repeat it?
So the idea is that if you have secret sharing, then you often want to do something like MPC, and with RSR, like this MPC is really good because in Shamir secret sharing, you need to do those degree lowering steps, and with RSR, you just do it. So it would be like really cool if we could have KRSR for arbitrary K, but this sounds too good to be true. So I'm asking whether you know about any impossibility results about that.
Yeah, so this question is more about what is how well do we understand the class of RSR functions itself, right? Like, as you mentioned, if we have a function which has KRSR, it can be useful for doing MPC as well. You can think of the U values as secret shares, right? Yes. So it's not clear, at least it's not from what I have read, it's not clear what the landscape of RSR is. And yeah, so.
Thank you.
Any other questions? Okay, let's thank Amit again. And now we have a coffee break and the invited talk at 11:05, right?
The coffee
11:05.
break is the same place as breakfast, and all the desserts and stuff are ovo-lacto vegetarian for those who are interested. And I mean, again, please don't bring food or drink back to the conference hall. Enjoy.